Hey everyone, so this is the audio lecture for Module 8 on energy and its interactions. So as we talked about before the midterm, right, we learned that energy is the ability to do work. And this concept I think is kind of intuitive, right? Imagine having to, do a marathon, right, on an empty stomach. Right? Without energy, you won't be able to do work. So again, the energy is what's going to allow us to do the work. Mathematically, the symbol's E, which again, pretty simple, E for energy, and the units are joules, which again is kilograms times meters per second times meters, or meters per second square. So this first law of conservation of energy is maybe one of the most important concepts that we learn. Right? It simply states that energy cannot be created nor destroyed. It can only be transferred or transformed from one form to another. Right? So another way to say that is the total energy is constant in a system, right? And that could be large scale whole universe, right? The energy in the whole universe is just a finite number. Right, and we can't add to it and we can't subtract from it. All we do is observe and transform one form into another. Okay, and I'll give you an example. Right, this is how important it is to actual ultrasound physics. A ultrasound probe, right, an ultrasound transducer, the tool that's used to form the ultrasound images, it's really just a tool that transforms the electrical current, right, that we get from the wall, right, and transforms it into ultrasound energy, which are basically ultrasound waves, into the body to create the images. All right, so it's a closed loop, but it also transforms this ultrasound energy that echoes back into the transducer and forms an electrical current that then the screen can use to form an image, right? And again, you don't have to understand that yet, but just again to give you an idea how important it is for our field. And another thing just to remember is that, again, energy cannot be created from nothing, right? So you need to have the energy from somewhere, and usually it's just transformed from one place to another. And when we talk about that, there is a type of energy that's almost invisible, right? And again, we call this potential energy. So this is, again, stored energy that's not actually doing work, but has the potential, as the name implies, to perform work. Right? This energy contained within a system because it has the potential to do the work, and is usually depends on the relative point between a reference point and the position of the object. So I'll give you some examples, right? You have electrical potential energy, right? Think of an outlet, right, that has the electrical potential. Now, it's not going to do work until you plug something in or until you flick the light switch on, right? But that's a potential energy. Another one could be elastic potential energy, right? The example I give is a bow and arrow, right? You draw the bow, you draw the string, and you are basically adding or putting potential energy into the arrow as you pull it back. The farther you pull, the more potential energy stored, right? And then as you release it, we know again that it has the ability to work because, again, this arrow will be shot out with incredible speed sometimes, right? But really when we talk about potential energy, the majority of the time, we're going to be dealing with gravitational potential energy, right? And this is what we'll cover in this next slide. So as the name implies, it's stored energy of an object by virtue of its height above the Earth's surface. And the reason that it depends on the height is because gravity is what's given us this energy, right? So that's why it's called gravitational potential energy. The higher above the Earth's surface, the more gravitational potential energy the object has. But it's also going to depend on its mass. So again, an example you often will see in books and other sources is a book on a shelf, right? So a book on a shelf has potential energy because it's above the Earth's surface and has the ability to do work if it falls to the ground. So the taller the shelf or the table that is sitting, the more potential energy it actually carries. But it's also going to depend on the weight of it, right? Think of a falling small pamphlet versus a falling large heavy book, right? Which one's going to make more noise? Which one hurt most if it fell on your foot, right? The heavier book, right? So those are the two concepts. And when we look at it mathematically, it makes sense. Okay, so this is the equation. Potential energy, right, of falling objects are calculated by multiplying the mass of the object times the acceleration of gravity on Earth, which again, we know it's a constant, right? This number, 9.8 meters per second squared. And then multiplied by the distance or the height above the Earth's surface. And again, so we have on the right here a picture of a weight suspended, right, by this sort of crank system, this levy system that pulls the weight up, right, and holds it up. And we know it has potential energy because if we were to cut that string off, this weight would fall down and actually drive this wooden stake into the ground. Now, when it does that, it transfers the energy or transforms it from a stored energy into an actual moving energy, which we'll learn about next. That's called kinetic energy. But again, the higher it is and the more mass it has, the more potential energy is stored in the system, right, in this object. Now, I asked, what are some other examples, right? And the big one that I can think of that I think most of us would relate or have experienced at some point or another is if you've ever been in a roller coaster, right? Think of Great America. Think of just the old school roller coaster like the American Eagle or the Viper, right? Which are really just like railroads, right? That are formed into loops and twists. And really the only mechanical aspect of a roller coaster is that first drop, right? So if you've been on a roller coaster, you'll hear the crank of the mechanical, the mechanics as it pulls you up that first ramp, and you go up this tall ramp. And if you notice, any roller coaster, the first drop is always the highest, right? Is the tallest part of the roller coaster, and that's on purpose. That's because you want to create as much potential energy. Not create, but I should say you want to store as much potential energy into a roller coaster so that once it falls off that first drop, it's all kinetic energy. It really, there's no other mechanics. It's really just a cart on a track, right? And the rest of it is all the loops and twists and turns are all driven by the original gravitational potential energy of of being this high above the Earth's surface. All right, so that's the example I could think of. Let's do a quick example problem, right, for potential energy. So the question is, what would be the potential energy stored in an elevator that weighs 1,000 kilograms as it hangs 100 meters above ground level, right, above the Earth's surface? This would be the point of interest, right? So again, once you memorize this equation, mgh, you just plug in the number, right? The mass. We know this is the mass measured in kilograms. So it's going to be 1,000 kilograms multiplied by the acceleration of gravity, which we know is 9.8 meters per second squared, multiplied by the height, which we said was 100 meters. So again, really, you don't need a calculator. You're just going to start moving decimal places, right? 3 to the right when you multiply by 1,000, and then 2 more to the right when you multiply by 100. So you get a number that's 980,000 kilograms times meters per second times meters, or also known meters per second squared, which again, we call joules to simplify. And again, anything that has potential energy has the ability to turn that energy into kinetic energy, right, into actual moving energy. So that's the next concept, naturally. And again, kinetic energy, or KE, is the energy that an object has by virtue of its motion. Okay, it's energy contained in anything that's moving, in any moving mass. So if something is moving, it has kinetic energy. And we can measure this kinetic energy. Here's the equation, right? It's 1/2 or 0.5 multiplied by the mass of the object multiplied by its velocity squared, okay? And this isn't to confuse with acceleration. It's not really acceleration. We are measuring the velocity, but it's a velocity squared. So we know velocity is going to have a higher impact on our kinetic energy, but so has mass. So the more something that weighs more is probably going to have more kinetic energy, right? As long as the velocities are equal, the heavier object will have more kinetic energy, right? Think of a moving train. But the velocity at the end of the day is the variable that has the greater impact. So the amount of kinetic energy an object has depends on the mass as well as the velocity, again, because those are the two variables in the equation. So let's do an example. All right, so determine the kinetic energy of that 1,000 kilogram elevator. So now we've dropped that elevator, right, off its suspension, and imagine it's falling at a speed of 50 meters per second, okay? At the velocity of 50 meters, I should say, of 50 meters. We know it's dropping down, so we know it's an actual velocity measurement. All right, what will be the kinetic energy at that point? So again, we got our equation, 0.5 mv square. Sorry, there should be a square here. And then we get, again, it is 0.5 multiplied by 1,000 kilograms. So we know it's going to be 500 multiplied by 50 meters per second squared. Okay. So again, this is another typo. This shouldn't be meters per second. It's actually, we're actually squaring the value, right? And not the units. We're gonna square the value. So 50 squared is 2,500 meters per second multiplied by 500 kilograms. And again, so when we multiply these two numbers together, we get 1,250,000 joules. All right. And again, sorry, I had to edit this because it wasn't originally like this in the PowerPoint that I posted at first. So my apologies. I've edited this and I'll make a note of it. I didn't realize it till after I reviewed it. So anyways, just for the quiz, it's fine if you don't square it, but just again, remember from now on, right, that velocity is squared. So we're going to take whatever our velocity is and multiply by itself, right? So we could square it. And so this is going to make a very, this object has a lot of kinetic energy, as you would imagine. Now, I make this distinction. I don't know if I've talked about this before. We keep mentioning mass, right? And then we give units of weight. But just remember that it is the mass of the object and not the weight, even though that's how we measure mass here on Earth. Because again, think of objects out in space, right? That may even be considered weightless, right? If you're far enough from the Earth's gravity, you could actually be weightless. However, if you are moving, you still have kinetic energy. Why? Because even if you're weightless, you still hold a mass, a certain amount of mass, right, in an object. And so that's why we make the distinction that we're measuring mass as the variable, right? We're not, even though, again, we measure mass in kilograms here on Earth, you can measure mass as something else. Even if you're weightless. So the rest of the PowerPoint, I think, is a little more simple. Rather than concepts that hold mathematical equations, they're really just some stats, right? Some facts on a different kind of energy. So here's another kind of energy that you'll come up with, and we talked about this before. So chemical energy is the kind of energy that's stored in chemical bonds and released by way of chemical reactions, right? So even the fact that we can perform work by storing energy in our cells, right, in our tissues of our muscles, that's actually a type of chemical energy, right? The way batteries store energy inside its cells, which then can power our devices. That's a chemical energy, all right? A bomb is a type of mechanical energy, right? That's released through chemical reactions. Another kind of energy is electrical energy. And remember, all these can be transformed from one to the other, right? Just giving you the different types, at least the most important. So electrical energy is energy due to the separation of charges and the flow of electrons. Now, this energy performs work when this electron or this electric charge moves through a potential, like a wire, right? So you need the separation of charges, and then that creates the electric charge, right? That actually does the work. So that's electrical energy. Nuclear energy is energy contained in the nucleus of an atom, right? Usually released as bonds are broken. And really, I'm not a nuclear energy expert, so think of nuclear generating plants, right? Which will sometimes use things like isotopes or other other energy forms to create electrical current, right? So they're transforming nuclear energy into other forms of energy for our use. We have thermal energy, and thermal energy is energy that's given off as heat, right? So anything that causes friction is a type of thermal energy. And again, this energy is caused by motion of the atomic or molecular level. So this is actually kinetic energy of atoms. And now the faster these atoms and molecules move, the more thermal, right? The more heat that it produces, and therefore the higher the temperature. All right, and again, we measure thermal energy by a temperature gauge or a temperature scale, which we'll talk about at the end. All right, but again, for now, thermal energy is energy given off as heat. So again, a little more on heat. We said, it's the kinetic energy of molecules, right? And it's usually shows up as a random disoriented motion of these molecules. And again, the more rapid and disoriented the motion, the more heat produced. Again, the energy absorbed from ultrasound beams is usually converted into heat. All right, although it might be little, it is basically how ultrasound energy is sometimes lost, right? It's converted it to heat. The other way that I think about this random disoriented motion of the molecules is I think of when you boil water, right? If you ever put a pot of water, right, in a stove, and as it starts to heat up, water actually literally bubbles. And again, this is that disoriented motion that we can actually physically see, but this is also happens when the temperature isn't that hot. We don't see that because there's not as much motion. All right, so that's basically what's happening. This boiling motion that you see when you boil water, that's what happens at a molecular level when heat is dissipated. And again, we measure heat as units of calories, right? So think of, again, if you work out, you'll measure the calories you burned. It literally is the amount of heat produced by the exercise that you do. Now, heat has different effects on different materials, right? So heating up water is much simpler than heating up something solid, right? For example, I give the example here, to change the temperature of just 1 gram of silver by 1 degree Celsius takes only 0.5 calories. But if you wanted to change the temperature of that same amount of water, it would only requires 0.0025 calories, so much less, right? And again, this is us transferring heat, right? Creating this temperature change. So we should talk about the 3 ways in which heat is transferred. Okay, so we'll talk about each one of these. So again, heat is transferred in by way of conduction, convection, and thermal radiation. All right, now explain each one of those. So start with conduction. Conduction is the transfer of heat by molecular motion from an area of high temperature, right? So the part that's rapidly vibrating, like I said, the higher the temperature, the more motion there is. And it transfers from an area of high temperature to an area of low temperature where there's low or no vibration. And then this is actually performed through the changing or the transferring of kinetic energy of the vibrations. So think about if you had a fire, like a bonfire or fireplace, right? If you actually had a fire and you had a metal rod, right, a metal poker, and you put the metal end on the fire and you held the other with your hand, you probably know, I'm sure just from experience, right, that if you were to hold that metal rod, even though it's not touching the flame directly, right, it's only touching it through the other end, that you'd eventually feel the heat on your end. And in fact, it could potentially burn you, right? That's why most metal pokers, right, used for fireplaces have a wooden handle, right, in order to keep you from getting burned, because we know that there's conduction, there's heat transfer from the hottest part of that rod to the other end where there might be, no vibration. And again, that's because this friction causes a domino effect, right? So you have molecules vibrating on one end, and that causes energy to be transferred to its neighboring molecules. Again, eventually moving to the other end where there's really no vibrations. So again, conduction requires conductors, right? And conductors are things that allow us to transfer this energy from the high temperature to the low temperature area. So things that are metal are good conductors, right? Things that are made out of copper, aluminum, silver, etc. Those are going to be good conductors. Here's again a picture of a fireplace rod, or poker as they're called, right? You'd want one with a wooden handle, or you want one that's not going to stay on the heat for long or on the fire for long, right? Because eventually, again, you're going to feel it on the other end. Now there are other products or materials that are bad conductors, things like wood, certain papers and things like that. We call those insulators, right? The insulation material in your home is made such that it doesn't conduct heat, or cool. It just doesn't let the temperature or the heat dissipate. It holds it in. And again, because it's such a bad conductor, right? That it actually insulates. So again, that's one way that we can transfer heat, right? Conduction. The other way that we can transfer heat is by way of convection. And convection is a physical transferring of hot molecules, usually done in gas or liquid form, from one place to another. And the way it happens is that when fluid or gases become warmer, their molecules expand, making them less dense, right? And these molecules will then rise to the top. And again, we know that, most homes are heated this way now, right? So if you have a forced air furnace at home, that's how it's heating up your home. It's actually heating up liquid in your furnace, and then there's a fan that pushes the hot air through the vents in your home, right? So hopefully it'll heat up the entire home through these ducts. So that's where the mechanical transfer of these molecules are pushed or transferred. All right. All right. Now temperature, again, is usually measured with a thermometer. All right. And again, so when we talk about heat, we talk about measuring the amount of heat and what it does to temperature, changes temperature. And so if we measure with a thermometer, we'll notice that there are two reference points to every thermometer. And for pretty much any kind of thermometer we use, we have two reference points. And the reference points are usually the freezing point of water and the boiling point of water, right? And we do that because those are, water is the most common molecule in this world, right? So it's easy to gauge that. Now, there's three scales that I kind of want you to know about, right? One is Celsius, which is really, the most widely used temperature scale, right? If you've ever lived in another country other than the United States, or your family comes from another country, you'll probably know that that's the temperature used routinely, right? For weather, for your body temperature, right? It's measured in Celsius. And even in this country, Celsius is how we measure the temperature of people in hospitals for other medical purposes. In science, that's how we measure and notate temperature of most liquids. Now, Fahrenheit is another temperature scale, and it's one that, again, we use the most in this country, right? When we talk about the forecast or the weather outside, we're usually talking about that temperature in Fahrenheit. And so we know 32 degrees is the freezing point of water. And you may or may not know that 212 is the boiling point of water. So if a liquid is 212 degrees Fahrenheit, it is boiling at that point, right? And then everything in between is broken down in equal segments, right? And same thing with Celsius, except 0 is used as the freezing point and 100 as the boiling point. And so that way you have equal 100ths in between, okay? And another scientific scale used is called the Kelvin scale, usually used to measure light temperatures. And again, things that are either very, very hot or very, very cold, right? So if we measure perhaps, the temperature in another planet, for example, then you might hear about it in the Kelvin scale. And again, so the freezing point is 273, and the boiling point is 373, right? So again, this is used for pretty large scale things that fluctuate in temperature a lot. And again, more than anything, light, because light emits a certain temperature. It's usually measured in the Kelvin scale. Now, you don't have to know all this about them, but you should know if I say, this scale has 0 as the freezing point and 100 as the boiling point, you should probably know that I'm referring to the Celsius scale. Same thing with Fahrenheit. And again, Kelvin's kind of easy because it's just that kind of wacky high numbers, right, on the scale. And then again, more importantly, all these three numbers refer to the freezing point of water, right? So you should know what the reference points refer to, right? And the top number is the boiling point of water. So again, all three of these scales have the reference points that use water boiling and freezing as the two markers. All right, so make sure you know that. And that's it. Okay, again, as always, if you have any questions, please email me or post in the in the boards. Thank you.